So we're dealing with projectile motion, and the way that we're modeling it is with parametric equations. So here's our situation. An arrow is shot upward with an initial velocity of 93 meters per second. We'll go ahead and underline that. At an angle of 48 degrees, so that's our theta. The 93 meters per second, that's its initial velocity. We've been writing VI in the formulas that they're going to show you. They're going to show V with the little subscript of 0, V naught. Did we talk about that yesterday? Naught? We did not. Okay, so it's actually V N-A-U-G-H-T. Sort of a British term. You know what they call tic-tac-toe in England? Noughts and crosses.
Never heard that.
Yeah, noughts and crosses. Anyway, so this is V naught. So if you hear me saying it, I'm channeling my inner Brit here. Anyway, so it's shot with this initial velocity, this angle with respect to horizontal, and it's shot from a height of 7 meters above ground. We sort of modeled that yesterday. If this is the path showing the y value with respect to the x value, sort of like you're standing off to the side and seeing them shoot this arrow here, that's kind of what it would look like. The horizontal distance x from the starting point and the height y above the ground of the arrow t seconds after it is shot are given by these parametric equations. So the x position as a function of time is v naught cosine theta times t. The y is negative 4.9 t squared plus v naught sine theta t plus h. Now, you might say, Mr. Goddard, that does not look like the equation that you showed us yesterday. Okay, first off, they've rearranged some things, but hey, they're giving you the equations, right? I mean, that's kind of nice. Just for continuity's sake, that h, they tell you a little bit later on down here, that's the initial height. In class, we called that yi, okay? So that's where that equation comes from. V naught sine theta t, that actually I did give you that to you yesterday. But this third term, the quadratic term, what I told you was 1/2 the acceleration times t squared, or I'll write it here, 1/2 times negative 9.8 t squared. Well, guess what happens when you take 1/2 and multiply it by negative 9.8? You get negative 4.9. I don't really like the fact that they just throw this equation at you with it. At least they should say negative, or they should say 1/2 and then a, or there you go, and then t squared. And then down, and then in the problem they can say that the acceleration due to gravity is negative 9.8 meters. So it's just another thing to plug in. But they don't tell you to plug in, I mean, they make you plug in V naught, they make you plug in this one. I don't know why they don't also make you plug that in as well, but anyway, let's go ahead and convert these formulas to this specific situation. So x as a function of t is going to be 93 cosine 48 degrees, and I'm going to put that all in parentheses like they did. That's a good idea. Times t. Here's my v naught digression. Y as a function of t is negative 4.9 t squared plus, so I'm going to plug in v naught, so 93 sine 48 degrees, we'll put that all in parentheses, times t, plus, we underline it up here, h, the initial height, 7. So negative 4.9 t squared plus blah 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 t plus 7. Let's let our mathematical background help us out here. What type of equation is this? Something squared plus something times t or x plus another number. It's a quadratic, right? What does that graph look like? Remember what a quadratic graph looks like? Yeah, it's a parabola. All right, it's either opening upward, like a cupward, or downward, like a frownward. Okay, so frownward. That actually is this one opening up or down? Down like a frown, because the t squared term here is negative, okay? And that kind of matches this. Now, but this graph right here is a graph of the path at, you know, like if we were to look at it, after the arrow has traveled 1 meter, then it's at this point. After it's traveled 1 meter, it's like that. So this graph right here, y as a function of time, would look something like this. It's a parabola opening downward. It's going to look something kind of like that. Almost identical to here, okay? Like, what are the differences between these two? Yeah, it happens to be a little, that's just kind of the way that I drew it. This graph is a function of time. This graph shows both the y and the x as a function of x. This is like if you were looking at the graph, looking at the arrow flying through the air. This would be as if you're plotting the height values as we're going around here. So like at time 0, it's here. At time 1, it's going to be here. At time 3, it's up here. At time 7, it's over. See what I'm saying? So this is showing the height as a function of time. Might as well just talk about this last one. Keeping in mind that 93 cosine 48 degrees is a number, what does this look like? X equals number t. What type of equation is that? Like x equals 5t. What kind of equation is that? It's not a quadratic equation. Do y'all know the types of equations? Polynomial, linear, quadratic, cubic.
Is it linear?
It's linear. It's a line. X equals 5t. Alright. Everybody stand up. Go ahead and go, I don't know, touch the back wall, then come back, sit back down. Maybe stretch your arms, maybe spin around, come take a seat. Y'all are. Do a little dance. Alright, here we go. So, this is a linear function, okay? X is equal to something times t. So if we were to graph x equals 5t, that's going through the origin, it's got a slope. There, this right here, if we graph that, x as a function of time, that graph would look like this. Starts off at 0 and it's going to have some sort of slope like that. Now, got some different graphs, got some ideas. Let's go down here and see what the problem asks. How long is the arrow in the air before it first touches the ground? Let me say that again. How long is the arrow in the air before it first touches the ground? Okay? That would correspond to when the arrow is right here. Okay? This is when it hits the ground. Which one of these other two graphs and equations, the y or the x, is going to help us out to know when it hits the ground? The y one, right. In fact, if we look at here, the arrow will hit the ground at this time right here. Arrow hits ground. But I just want you to know, if this number right here happens to be like 1,000, that's going to tell you the arrow will travel 1,000 meters before it hits the ground. If we have something like here that says like 20, then this tells us that it's been 20 seconds until it hits the ground. Does that make sense? So I just wanted to kind of show you. But because of the way that the projectile motion looks, it looks upside down parabola, and graphing the height, it's an upside down parabola. So it's kind of neat and nice that they match each other. There's other things. At time 0, its y height is 7. At time 0, its height is 7. Also, when it's at its highest point here, it also corresponds to the time in which it's going to be at the highest point here. Stuff like that. So really, this graph is going to tell us all kinds of information, and we are really going to focus in on this graph over here and its equation. So for that purpose, I'm going to write it a little bit below here. So y as a function of t equals negative 49 t squared plus 93 sine 48 degrees times t plus 7. We were looking yesterday, sort of the very end of class, at the parametric graph, y is a function of t and x is a function of t. And I don't know, we didn't really get to this in this class, in my other class. We were trying to find, is there a way that we can figure out where that 0 is? And unfortunately, there's not. Not in the calculator, not in Desmos. With parametric, if you're in parametric mode, cannot find that point. However, if you are in functional mode on your calculator, and you have y as a function of x, and you just replace this t with an x, so negative 49x squared plus 93 sine 48x plus 7, okay? Do you all know how to find the x-intercept, also known as a 0?
Mm-hmm.
That's what we're about to do that here in a minute, okay? So let's go ahead and, well, I mean, you might be able to, I don't know, can Desmos find zeros?
Can't you just click on it?
You might be able to just click on it. What about the maximum, though? Can you find a maximum on Desmos? I do not know the answer to that question. John, while we're typing this in the calculator, can you figure that out for us? See if Desmos can find the maximum value. The rest of us, you're going to change your calculator to function mode, and we're going to type in this equation, but even though all of us know that the independent variable here is t, we're going to use x because that's just what our calculator has available to us in function mode. Yeah, I do. Yep. Thank you. This is kind of like what we did yesterday. Let's go ahead and hit zoom standard.
Oh, just put in that equation.
And zoom standard should probably give you something that's not very helpful.
Is that 4.9 or 4.9?
Yeah, you can look down, got it from previous class.
Yeah, because I was like, it's already on here.
Yeah, perfect. Hit zoom standard because that's going to be more likely the situation. Y'all typing it in? Okay. I need to make sure that like 99% of you have it typed in. Give me a thumbs up when you do. Okay, that's 99%. What we need to do is we need to talk about, once again, very quickly, how to find a good graphing window, okay? A friendly window. So, I recommend that we make our x minimum something a little bit to the left of the y-axis so we can see that. So, I recommend maybe -5. Our x maximum needs to be a little bit after it hits the ground, or the moment it hits the ground, which would correspond to the time value, or the x value, where the y values go from positive to negative, okay? We're going to need to look at the table for that. So we're looking at the table to figure out where the y values go from positive to negative. I know the answer, so you can just kind of shout it out here. Should be 2. Make sure your calculator's in degree mode, where the y values go from positive to negative. Let's look at your equation. Makes 49x squared. 93 4.9. Sorry. Negative 4.9. I wrote 49.
Is the maximum something they're asking us to find, or is that what you were doing extra?
We're going to do that at the very end. Well, the question we're asking right now is, how long is the arrow in the air? And the answer to that question, how long is the arrow in the air, is going to refer to this time value right here. It's sometimes known as the x-intercept.
The 0.
It's also known as the 0. It's also known as the root. But we'll call it 0. Does that help?
Yeah.
What number do y'all get now?
15.
I'm here at 15.
Yeah.
When the y values pass from positive to negative. Okay? That's good. Let's go ahead and, I don't know, let's kick it a little bit more over. Let's just say 20. 20 for our x maximum. Okay? Our y minimum, if you look up here, your y minimum is going to correspond to the lowest y value that's present on the graph. I normally like to be able to see the x-axis, so I make my y minimum like -5. And then we want our y maximum to be something that's going to be higher than the highest value that the highest y value that we're going to get. Okay? Like, how do I know the highest y value that I'm going to get? Anybody have an answer to that question? Okay, she's getting that from the table. So let's go ahead and look at the table during this range of values between 0 and 20. The biggest y value that you see on your table is around, you said 250?
250.69.
250.69. So let's maybe bump this up to maybe 260 for our y maximum. That will be able to give us, you know, hopefully this entire graph will be able to show up in there. We did this yesterday, but I also want to make sure everyone's aware of this. We're using the table to kind of match that. Yep, yep. Yes. Jeannie, do you know how to find the 0 here?
Yeah.
Can you walk me through that process really quickly?
Okay, so you do second, trace, and then you would click 2 or go down to 0. Right?
Okay, so you're going to go to the calculate menu. Your calculate menu is second trace.
Mm-hmm.
And then you then you choose the 0 option, and then it's going to give you the option for it to move your cursor around, right?
And it'll ask for a left bound and a right bound.
You want to move the cursor so that the left bound is somewhere to the left of the 0, and hit enter. And then you want to move the cursor a little bit to the right so that, as for right bound, your right bound needs to be somewhere to the right of the cursor. Because what your calculator is going to do, it does not know where to find the zeros. You have to tell it, look between here and here. And the calculator is actually going to play a game, programming students, in case you're curious. You tell it here and here, it's going to pick the value in the middle. If that value is positive, then it's going to pick in the middle between here and here. And it's going to pick that value. And if that value is negative, it's going to pick the value between here and here and evaluate it and see if that's negative. And then it'll compare it to 0. It'll continue to do that process until it cannot tell the difference between the number it's calculated and 0 due to the lack of precision. So anyway, that's how it literally zeroes in on it. So you have to have something that's positive and you have to have something that's negative for your left and right bounds. Okay? I'm going to walk around. I need everyone to show me that you can find that 0. Otherwise, you're toast. 14.2. What do y'all get?
I got 14.22.
14.21? 14.21? Yeah, because they're one nearest 100. You get it? Alright, Rosa? Max on Desmos?
Not sure.
They weren't getting our X's. Okay, now
So go to the second
to
then.
find your maximum, you're gonna do your second trace. You're gonna go to your maximum.
Hit the left right arrow.
Second trace.
You can do it here.
So hit the right.
But
We're gonna go. Right arrow is right to the L.
It is asking for left bound, you're gonna put insert.
Nope,
Zero, no left.
then you're gonna hit the, that's the left bound. We're zeroing in on the spot. That's fine, hit the right arrow.
Just guess.
We're gonna keep doing that until the cursor, then I'm looking here at a Y value, that's because you can't see it, it's actually kind of in that here. That's a good spot.
Did you click on zero or maximum?
Then actually,
Oh, I thought you were doing maximum, okay. When you click on zero, move the little cursor.
Ashley, did you get 14.21?
This is zero, zero, where your X crosses, correct? Okay. So on the left side, insert, now you're gonna go over.
Negative 5, Q, E to Y equals.
And that's your zero. 14.2, so that's your time.
Squared. Not 4.9 squared, 4.9 T squared.
What? It's so long. What are you freaking out about?
Okay, so, how long is the arrow there? We found out that it equals, what was that number, class? T equals 14.21 seconds. That's how long it is in the air, okay? Now, I'll see if anybody can answer this part B. What is the horizontal distance the arrow travels before it touches the ground? So in other words, just wanting to know how far it goes. Which one of these formulas is going to help us know how far it goes?
The X and T.
Yeah, the X and T formula. The one that was X equals 93 cosine 48 degrees times T. Let me say that again. If you want to know how far it travels, then you use the X formula, because that tells you the position at any given time. What time are we interested in evaluating this at? 14.21. Let me say that, make sure everyone's with us. We want to figure out how far the arrow went, okay? After 14.21 seconds. So that means I'm literally just going to plug in 14.21 into my X equation. So 93 cosine 48 degrees times 14.21.
So we don't need to use a graph, we just plug that in. Okay.
That is correct. You do not need the graph. We're just plugging the value, the time that we found into the X equation. And they're happy with us rounding this one to the nearest whole number.
884.
Say it again.
884.
884. Did we get a better graph?
Do you understand how to put in place?
Okay. And you're able to find the zero?
I know how to do this
Okay.
and that.
I need somebody to ask me a question on the process that we just did. Another question? We found the zero on the Y graph, and then we used that time value to plug into the X formula to figure out how far it travels. Does that make sense? Okay? Now, this is one variation, okay? The other variation is going to look, you can see there, it'll ask something like this: how long is the arrow, the ball, or whatever, in the air? Oh, hold on. That's not the one you're looking at, number. How long, gosh, there's another type. I know it's here somewhere. When does the arrow, or whatever, reach its maximum height? And what is that maximum height? Okay, so this is another variation. I figure we might as well just answer that question right here. So the first question is, when does it reach max height? Well, clearly it's going to occur at this spot right here. And we know, based on what we saw before, that's going to occur at the maximum of this graph. Now you might think, oh, I can just hit the trace button and see the biggest one. No, because when you hit the trace button and you hit left and right arrow keys, that's only going to give you at discrete locations. Like it's going to give you here and here and here and here and here and here and here. And there's no guarantee that one of those points that it's going to give you is the actual factual highest value. It's the same thing if you're looking at the table. If you look at the table, it's only going to tell you what it is in whole number increments. There's no guarantee that the maximum height is going to occur at a whole number time value. It might be at 5.12 seconds. You know what I mean? So not necessarily at 5. So does anybody know how to find the maximum using the calculator? It's using that same calculate method or calculate menu that we just went to. So you get the second trace, it takes you to the calculate menu, okay? And when you go there, one of those options says maximum. All right? You ever messed that before? Nia? Okay, that's why I'm teaching you how to do this right now. So hit the second trace button, take you to that calculate menu, and you want to go down, choose down to the option that says maximum, and then you're going to use the left and right arrow keys to, once again, we want to set a left endpoint that's a little bit to the left of what we know where the maximum is, and then you move that cursor and hit enter, and move the cursor a little bit to the right of where we know the maximum should occur, and then you can just hit enter, and when it says guess, you can hit enter again, because the right endpoint is just as good as any. And it will actually, through a process of process of iteration and calculation, figure out what that maximum point is. All right, so let me see your calculators. He's got the max. She's got what's her time value?
When you graph this, it's going to
7.05.
Correct. And you're not
Looks
going to be
good.
able to see what they need because you're in the wrong setting on the calculator.
So you know what you're
You're
doing.
going to go to the second table. And you're going to
Here, we got it?
and try to find the y maximum. Okay. But
Don't
the
think
biggest
so?
number is on
Okay.
here. And the biggest number
Okay,
is
different
on
here.
here is 50.
You got it.
So I went to
Did you ever use an
919.
output or anything like that?
Yeah.
From
Okay.
the window. And we know y maximum comes 250 up to 255.
All right.
So it's more.
So we have just realized that the maximum value occurs at, what is it, 7.05? And since, in this case, what we are using as our equation is x corresponds to actually t, the answer is it reaches it at 7.05 seconds. The follow-up question is, what is the maximum height of the arrow? Well, that's nice. We could just look across here and see what that y value is. What did it give you for the y value there?
250.
Max height is give me to the nearest 10. 250.7 meters. So basically, in this case, using the maximum feature, or the maximized feature of the calculator to find that max height. Okay? I know at the beginning it's kind of a little confusing because I'm drawing 3 graphs here, but I just want to make it very clear that this graph here is x and y as a function of time, sort of like if you were taking a video, this is what it would look like. But this right here is a graph of the y position, this graph of the x position. Okay? We really don't need this or this. This is the good graph. Okay? No need for us to do multiples of these. I have a lot written up here. Some of you have a lot of this on your paper. Some of you don't. If you want to take a picture of this mess, go for it. If that would be helpful for you. You have the rest of class to work on these problems.
Work on problems and also for future.